Hi guys, so this is the second part of today's chapter 10, theory of the firm, with the profit maximization problem, right, and cost minimization. So in the end, we introduced this production set, which is our primitive. This is analogous to the preferences. Then what do we do with preferences in the consumer chapter? We maximize them subject to a budget. Here we want to maximize profit subject to the uh, production set. Okay, firms, why they would like to profit maximize? Well, this is our assumption. So we are thinking of very simple firms that are price takers. They don't have market power. So conditional on taking price as given, they want to maximize profits. So what are profits? Profits are very simple here. It's just the multiplication of the vector of prices times the production plan. So notice that this is in fact equivalent to maximizing with respect to quantities and inputs, right? When you have the multiplication of the price of outputs, right? Times the quantity of outputs minus the price of inputs times the quantity of inputs. So in fact, this is profits, right? Because it's the subtraction of total costs from total sales, okay? But because of our notation is so efficient, it's just the multiplication or the inner product of the total vector of prices of all possible goods times the production plan, which has negative entries, which are captured here by this cost part. And so what is the restriction? Obviously, is that the production plan belongs to the production set. Okay, so not all things are possible, right? And this problem is going to have a maximum. Here I'm assuming it has a maximum whenever y has certain properties. In particular, if y is closed and convex, because it's a convex cone, and I can actually prove that this has a maximum. Okay, the proof that this is true is not only in this class, but you can check it in the Krebs book, and this is called the recession cone property, right? So notice that I'm not assuming that Y is compact, because it's not compact. Notice that by free disposal is unbounded by below, okay? But this set is a convex cone that is closed, and this is enough for proving that a maximum exists. Okay, so this is the mathematical parenthesis for the most advanced students. Behaviorally, what we're doing is basically this is a model of firm behavior, and this is a hypothesis of behavior. So the same thing as the utility maximization. So what do firms do is they maximize profits. Okay, what do consumers do? They maximize utility. Okay, that's the world model of the world. And in particular, let's write down the problem in calculus, which is what we want to do because that's easy to model. So let's use the transformation function for that. Now maximize profits subject to the restriction given by the transformation function, which means that capital F, the transformation function, evaluated at y, is less than equal than 0. So now, what is the result of maximizing profits? It's the profit function. So the profit function is the analogous of the indirect utility for the consumer chapter. So this is the value function of the maximization problem. That means pi of prices is equal to the maximum value of profits that is feasible given the production set. And the maximizer of this problem is called the supply correspondence. This is the analogous of the demand correspondence. So again, as in the case of demand correspondences, this is a set. So for a given price, you may have a set of production plans that maximize profits. Okay, so all of these production plans in the supply correspondence gives you the same level of profits. So it's non-uniqueness, right? A non-unique prediction. And also this profit function may actually be infinite. When is that the case? When you have non-decreasing returns. So when you have this case of explosive production, then of course you can reach infinity. That of course is not an interesting case in modeling, so we're gonna try to avoid it. But right now this is possible. Now, we want to do calculus, I told you. So by using the transformation function and assuming it's differentiable, we can do first order conditions First order conditions usually are very good to understand the problem, and this is what we're gonna do. So take a point in the supply correspondence. It has to be that there is some Lagrange multiplier lambda such that for this point in the supply correspondence, the first order conditions are satisfied. That means for a price of the good L, it can be an input or an output. This is equal to lambda, the Lagrange multiplier, multiplied by the partial of the transformation function with respect to the good L. And this has to hold for all goods. Or in matrix notation is the vector of prices is equal to lambda scalar multiplying the gradient of the transformation function. This is very similar to the utility maximization of first order conditions, right? But notice here that there is no budget, right? This is already giving you all the information you need, okay? So this problem is simpler because you're maximizing, this is more similar actually to the problem of cost minimization mathematically. Now, for the case of single output technologies, we have basically that you can maximize the quantity set by, which is the amount of inputs, and then you replace the fact that the Q quantity is equal to the production function at the frontier F of set. And then basically given the prices, this means that sales are equal to P times F of set. And this is minus the cost, W being the price of inputs. And then you have set the quantity of inputs. And then you choose the quantity of inputs to maximize profits. F is a production function, and now the first order conditions, allowing now for corner solutions, can be given by these following set of inequalities, which are the Karish-Kuhn-Tucker inequalities of this problem. So this is PL, the price of L, multiplied by the partial of the production function with respect to the input set L. This is less than or equal than the prices of the inputs WL. Such that with equality holds whenever the quantity of input is not in the corner, so it's actually a positive quantity. And then you also have these slackness conditions or Karish-Kuhn-Tucker conditions, complementary conditions. That means that this quantity here, which is the first order conditions before, is 0 whenever the set is positive. And when set is 0, so a corner solution, then you have the inequality in the first order conditions, okay? Now, if y is convex, remember convex is non-increasing returns, then the first order conditions are actually necessary and sufficient for optimality, okay? So first order conditions may not be enough to guarantee optimality when you don't have a convex set, okay? You also know that without convex sets or with increasing returns, you have explosive profits. So you don't care about that case. We care about the case of convexity. So, okay. So now we have the profit function and we have the supply correspondence. We're going to describe the properties of them. First, we again redefine them just for having them in the front, right? So this means that profit functions are the max value and the supply correspondence is the maximizer, okay? Assume in this proposition that the production set is closed, satisfies predisposal. Then, first, the profit function happens to be homogeneous of degree 1 in price. So let's go back to the definition. If I multiply prices by an alpha scalar, then what will happen with profits? Profits multiply by alpha, okay? So homogeneous of degree 1. That's very simple. Profits are convex. So what does it mean? So profits are a multivariate function of a vector P. The fact that it's convex on P basically means that this is the multivariate notion of convexity, which we study actually in this mirror image in the cost function, in the expenditure function in the consumer chapter, when the expenditure function was concave on prices. Here, the profit function is convex on prices, so it's the mirror image of this expenditure function. Basically, we have that if I take the matrix of derivatives of this, and then I take the matrix of second derivatives, which is called the Hessian, then the Hessian has to be positive semi-definite. Okay, so you can check this in Wikipedia. It's very easy. Okay, and this is a requisite for this class, by the way. So calculus 3. So if y is convex, then what we have is something wonderful, which is a characterization of the whole production set by means of the profit function. So this is very cool because basically this means that all the information about the production possibilities frontier can be captured by a scalar function profits in the following way. So before I told you that in order to know whether a production plan belongs to a production set, I have to know the transformation frontier. But the transformation frontier may be a very complex function, right? Also, if I give you the set of production set, it's very ugly, very complex object. It's a set. It's a huge set. So instead of that, what about if I give you just the profit function? And then it turns out that I can check whether a production plan belongs to the production set by doing the following exercise. Take one price, multiply it by the candidate production plan, and then check whether this is less than equal in terms of money to the profit that this firm is making at this price speed. Because profits are maximal, any feasible production plan has to be slightly below or exactly equal to the profit. And this happens for all prices. So if I do this, then this is a linear program to check, very easy computational. I can verify whether y belongs to the production set, okay? And this is actually a very important observation that is going to be useful in what comes. But remember, this is about reduction of dimensionality, the same idea we use in utility maximization. In utility maximization, we have the Royce identity. Here, we're going to have something very close, which comes in a second. Now, properties of the supply correspondence. Y of P is homogeneous of degree 0. So if prices are scaled by alpha, is still the same maximizer. So let's go here and let's try to multiply this objective by alpha. Then the first order conditions are the same. They don't depend on alpha. So that means that the supply, the quantities are the same. Okay? Relative prices are the same. This is the same as in the utility maximization problem. The only thing that matters is relative prices. So because relative prices are the same, then the supply is the same. Now, if the production set is convex and Y of P, the supply correspondence is also actually convex. Again, this is important because you fix a price and then you have a set of possible supplies, right? So you want them to be convex because then you can only study the boundary of this to characterize the whole set. So it's good mathematically, but also we're gonna kind of use it later. But the real important thing for modeling is that if Y is strictly convex, so your returns are actually decreasing instead of non-increasing, then the supply correspondence is single value. So you only make a supply function. Okay, that's important. And now we have the analogous of the Royce identity. So if Hotten's lemma, if the supply corresponds of a single point, so a supply function, and the production function is differentiable, then if I take the gradient of the profit, this is equal to the supply function, which is great, right? Because you again show that this is a huge reduction of dimensionality. So you have a huge vector of 100 of outputs, 100 of inputs. All of them can be characterized by a profit function, which is a multivariate function of all prices. That's fine, but it's a scalar function. So you take the gradient of that, which means the partials with respect to each price, price 1, price 2, price so on, and then you put it in a column. That gives you the supply. Okay, amazing. So this is basically the basis for our next result. So if the supply function is differentiable at prices, then the substitution matrix of this supply function is equal to the Hessian of the matrix of second derivatives of the profit function, which is by definition of continuity of the profits and convexity of the profits, is a symmetric and positive semi-definite matrix such that is also singular in prices. So this is actually the Slowski matrix version here in production set. So I'm going to prove it. And the proofs are very similar to what we saw at some point in the case of the expenditure function, right? So here we basically show that if you have a convex function and you take a convex combination of two supply plans, basically two prices, you combine them in a convex way and you see the supply associated with this, then you basically have this particular new supply. And convexity means that if I take the profit function evaluated at this convex combination of prices, this is less than equal than the convex combination of the profits at the price P and price P star. This is just the definition of convexity. Now, how do I prove it? Well, it's very easy. I just take the definition of profits. Profits is prices times the supply function. So by definition of profits here, this is equal to alpha of P times 1 minus plus 1 minus alpha P star multiplied by the supply evaluated at this particular intermediate level. Now, by definition, these quantities here, the supply, has to be, of course, as you can see, dominated by the profit generated by the own supply at a particular prices P. So putting this line together here above, it means that an upper bound of this is alpha of profits of P plus 1 minus alpha profits of P prime. So showing this is convex. Okay. So now if Y is convex, then by definition I have that for any price multiplied by the production plan, this has to be, of course, below the production plan, which maximizes profits, right? And now it happens that because you are convex, you can actually describe all this set by means of these supporting hyperplanes. And the final part just follows from the envelopes theorem. So I write a Lagrangian problem. I derive it with respect to prices, and I obtain the supply. So you can see here that the only part that it depends on prices is this part. The envelopes theorem tells me that I can derive this as supposing that y is constant, so I do it, and then I have here yp. And the final part is just a consequence of this typical just derivation, okay? So this is the final and the end of the proof. Now, notice that the final property in terms of non-differentiable terms gives you the law of supply. So the difference between prices P and P star vectors multiply inner product between the difference of supplies or production plans Y minus Y star has to be greater than or equal than 0. So positive semi-definiteness is equal to the law of demand. So I want to quickly go to the property about supporting hyperplanes and how they describe the production set. So I'm going to describe the production set graphically. So here you have outputs, and here you have inputs, right, with a minus. And imagine this is a production set. So this production set is the shaded area with blue, okay? So this is the production set Y, okay? And now the fact that this firm is profit maximizing means that I'm choosing a particular price P, and then I'm choosing the point that is in the frontier that maximizes my profits, right? So now imagine I have a different price, P star here, right? And I have different other prices and I keep moving them, right? Eventually they will start covering this convex object, right? Such that if I use all possible prices, eventually I will recover the convex set, okay? So this is called the support function of a convex set. And basically this means that geometrically the profit function is the support function of this production set, okay? So this is the second part. Thank you.